My respected students, my name is Dr. Fahmy, and today we're going to embark on a journey into one of the most exciting and transformative fields of modern science, nanomedicine. This presentation, titled Nanomedicine, the future concept, will explore how operating at the smallest imaginable scale is poised to create a giant leap forward in how we diagnose, treat, and prevent disease. We'll start by understanding what nano really means, delve into the core concepts of nanomedicine, look at what we have already achieved, and finally, peer into the future to see the incredible possibilities that are on the horizon. So let's begin by shrinking down and understanding the world of the very, very small. To understand nanomedicine, we first need to grasp the concept of nano. The word itself comes from the Greek word for dwarf, and in science, it simply means 1/billionth of something. So, a nanometer is 1/billionth of a meter. To put that into perspective, if you took a single meter and divided it into 1 billion pieces, each of those pieces would be 1 nanometer. That is almost unimaginably small. We're talking about the scale of individual molecules and atoms. Nanoscience and nanotechnology are the fields that study and manipulate matter at this minute scale, typically between 1 and 100 nanometers. And here's the most important part. Although this science revolves around very, very small things, its potential is enormous. At the nanoscale, the ordinary rules of physics and chemistry can change. Materials can exhibit new properties like different colors, strengths, or electrical conductivities that they don't have at our everyday macro scale. It's this unique behavior that we can harness for revolutionary applications, especially in medicine. This diagram helps us visualize just how small the nanoscale is. Let's start on the left with a water molecule at about 0.1 nanometers. That's the foundation. As we move to the right, we see a benzene ring at half a nanometer and then a carbon nanotube with a diameter of about 5 nanometers. This is our world of nanomaterials. Notice that a virus, like the one pictured here, is about 100 nanometers in size, placing it firmly within the nanoscale realm. Now, compare that to a red blood cell, which is much larger at about 5 micrometers or 5,000 nanometers. A human hair is even more massive, around 100 micrometers wide. And finally, a single full stop or period from a printed document is about 1 millimeter. So, when we talk about working in nanomedicine, we are operating in the space between individual molecules and the size of a virus. This is the precise scale of many of our body's own biological machinery, which is why it's so perfect for medical intervention. So, now we define our key term. Nanomedicine is the branch of medicine that applies the knowledge and tools of nanotechnology to the prevention and treatment of disease. In practice, this means we use nanoscale materials, often smaller than a single cell, for specific medical purposes. These materials, which must be biocompatible, meaning they don't harm the body, can include nanoparticles and even the futuristic concept of nanorobots. What do we use them for? The applications are vast. We can use them for diagnosis, to detect diseases earlier and more accurately. We use them for delivery, to transport drugs precisely to where they are needed in the body. We can use them for sensing, to monitor internal conditions, or for actuation, to perform a physical action, like breaking up a blood clot or cutting away a disease cell. In essence, nanomedicine gives us a new set of ultra-precise tools to interact with the human body at its most fundamental level. The ideas behind nanotechnology aren't entirely new. Did you know that as far back as the 19th century, we had a form of nanotechnology? They used nanoporous ceramic filters to trap and remove viruses from water, even if they didn't call it nano at the time. The modern conceptual foundation, however, is widely credited to the legendary physicist Richard Feynman. In his famous 1959 talk, titled "There's Plenty of Room at the Bottom," he essentially challenged scientists to explore the world of the small. He envisioned the possibility of manipulating and controlling things on a miniature scale. This talk is now seen as the intellectual birth of nanotechnology. It inspired generations of researchers, and ever since, the field of nanoscience has evolved at a breathtakingly rapid pace, leading us directly to the advanced nanomedicine we are developing today. Now, let's get into a practical application, creating nano-size carriers for drugs, a process known as nanoformulation. The methods to create these tiny drug carriers are broadly split into two categories. First, methods that require a chemical reaction to form the nanoparticle polymer on the spot. And second, methods that use a preformed polymer or macromolecule, which is then processed into nanoparticles. The choice of method is critical and depends entirely on the properties of the drug you want to encapsulate and the polymer you're using. A star player in this field is a polymer called PLGA. That's polylactic coglycolic acid. PLGA is a copolymer, a mix of polyglycolic acid and polylactic acid. It's a fantastic material for medicine because it's highly biocompatible and biodegradable. It's even been approved by the US FDA for use in pharmaceuticals. Why is it so safe? When PLGA enters the body, it slowly breaks down through hydrolysis into its original building blocks, lactic acid and glycolic acid. These are natural metabolites that your body already knows how to process, breaking them down further into water and carbon dioxide through the tricarboxylic acid cycle. This results in minimal systemic toxicity. We can create PLGA nanoparticles using techniques like the single emulsion solvent evaporation method, or the more complex double emulsion method. The rate at which it degrades and releases its drug cargo can be finely tuned. For instance, the polylactic acid part of the polymer is more hydrophobic, meaning it repels water. By adjusting the ratio of the acids, we can control how quickly water penetrates the nanoparticle, and therefore control the drug release rate, allowing for slow, sustained release over time. PLGA is just one example in a vast and growing toolkit. Nanomedicine isn't a single technology, but a collection of different platforms, each with its own strengths. Beyond polymeric nanoparticles like PLGA, we have liposomes, which are tiny spherical vesicles made from the same material as cell membranes, are perfect for encapsulating drugs. Nanogels, highly absorbent polymer networks that can swell with water. Polymeric micelles, which self-assemble in water to carry water-insoluble drugs in their core. Solid lipid nanoparticles, which offer a solid lipid core for enhanced stability. Nanoemulsions are mixtures of oil and water at the nanoscale. And even carbon nanotubes, which are tubes made of carbon atoms with unique electrical and mechanical properties. Each of these structures can be engineered for a specific task, whether it's targeting a cancer tumor, crossing a tough biological barrier, or responding to a specific trigger inside the body. So, what do we actually accomplish with all this? The progress has been significant and tangible. First, we have improved drug delivery systems. We can now design nanoparticles to deliver drugs more efficiently, directly to specific cells like cancer cells. This targeted approach reduces devastating side effects and improves the drug's efficacy. A prime example is liposomal doxorubicin, marketed as Doxil, which is a nanoscale version of a chemotherapy drug that reduces damage to the heart. Second, we have diagnostic nanoprobes. We've engineered nanoparticles to act as supersensitive detectives. For instance, quantum dots are tiny crystals that fluoresce with bright, specific colors, allowing for highly sensitive imaging to detect diseases like cancer at their very earliest stages. The applications are diverse, from transdermal and ocular drug delivery to regenerative medicine, where nanotechnology provides scaffolds that mimic our body's natural extracellular matrix to promote tissue growth. Perhaps the most futuristic achievements are in nanorobotics, where we are developing tiny machines capable of precise manipulation at the cellular level for targeted delivery and repair. And finally, we have theranostics, a portmanteau of therapy and diagnostics. This allows for a single nanomaterial to both treat a disease and simultaneously monitor how well the treatment is working, enabling real-time adjustments. If what we have now is impressive, the future is truly breathtaking. We are moving towards an era of precision medicine, where treatments are tailored to your individual genetic makeup. Nanoscale biosensors could monitor your biomarkers in real time, allowing your treatment strategy to be dynamically adjusted for your body alone. Theranostic nanoparticles will become even more sophisticated, acting as complete diagnostic and treatment packages that provide continuous feedback, making medicine more adaptive and personal than ever before. The field of nanorobotics holds the promise of autonomous nanoscale surgeons. Imagine tiny robots that can perform targeted drug delivery, repair damaged tissue from within, or even conduct nanoscale surgery, revolutionizing minimally invasive procedures. In regenerative medicine, nanomaterials will be key to rebuilding damaged tissues and organs. Advanced scaffolds and bioactive materials could lead to breakthroughs in treating organ failure or spinal cord injuries. One of the biggest challenges in medicine is getting drugs to the brain, protected by the blood-brain barrier. Nanomedicine for neurological disorders aims to solve this, enabling targeted delivery of therapies for Alzheimer's, Parkinson's, and brain tumors. Finally, the merger of biology and electronics will lead to implantable nanodevices. These tiny devices could monitor your health from the inside, deliver drugs on command, or even interface directly with your nervous system to restore function in cases of paralysis or neural disease. And that brings us to the end of our journey into the future of nanomedicine. From manipulating single molecules to the prospect of cellular-scale robots, this field is redefining the possibilities of healthcare. Thank you for your time and attention. Again, my name is Dr. Fahmy, and I hope this glimpse into the nanoscale world has been as exciting for you as it is for us who work in this field every day. The future of medicine is small, but its impact will be immense. Thank you.